Alright, so let's get started. Let's get started if you allow me to do so. We've already seen the infinite potential well, and we've derived the solution. So the potential energy goes to infinity at x greater than L and x less than 0, and it's 0 in between. And we've seen that the energy levels are quantized. And these energy levels are labeled by the quantum numbers n. And n varies from 1, 2, 3, and so on. And how many energy levels will we have in this infinite well? Infinite. Because there is no restriction on what the value of n could be. So there is an infinite number of energy levels that we can have. And the wave function, if the electron is in the nth level, the wave function is given by 2 over L under root sine of n pi x over L. And the energy is also quantized, so in the nth level the energy is n squared pi squared h bar squared 2m L squared. And if you notice, we calculated this energy using the Schrodinger equation and the boundary condition that the wave function has to disappear at the edges. But there is another way to find out these energies, especially the lowest energy. Suppose you only use the Heisenberg's uncertainty principle. So I ask you the question, if the particle could be an electron, a proton, a photon, neutron, atom, the Schrodinger cat, anything. If it's confined to exist within this region, then what is the uncertainty in the value of x? That what is the spread or the realm of possibilities for the solution? L. So your delta x is of the order of L. What is your delta p? It's h bar over 2L. So suppose the minimum momentum is equal to the uncertainty. This is just an estimate. This is P. So your minimum energy, E minimum, has to be equal to P squared over 2M. Right? Because there is no potential energy, there is only kinetic energy here. And this turns out to be h bar squared 2m L squared. So this is the same order of magnitude as the ground state energy level, where n equals 1. There's only a difference of pi square, which is about 10. Pi square is about 10. So it gives you the roughly the same order of magnitude estimate for the minimum energy this electron must have if it were to be confined within this range. So without solving the Schrodinger equation, just by looking at the power that uncertainty principle provides you, you can find out what the minimum energy is. And if this well shrinks in space, this minimum energy goes up. So that is also the uncertainty principle, which states that quantum mechanics does not allow you to squeeze systems. If you squeeze systems, the energies go up. So, and we can also plot these wave functions. For example, the ground state wave function looks like this. The first excited state has a wave function that looks like this. The second excited state has a wave function that looks like this. The third excited state, or n equals 4 state, has a wave function that looks like this, and so on. And can notice that the wave function is always 0 outside the well. At the walls it is also 0 because the boundary conditions have to be satisfied. And then there are nodes. For example, for n equals 4, there is a node here where the wave function is always 0. The wave function is 0 here. So if you measure where the electron is, if someone asks you the question, tell me where the electron is, you have to perform an experiment. When you perform the experiment and you have multiple copies of this system, you will never find the electron to be at L over 4 or half of L or 3 L over 4. You will never find the electron here because the probability density function corresponding to this wave function is like this. Okay? So there is maximum probability of finding the electron here, here, here and here if the electron were in the n equals 4 state. And the electron can of course make transitions between these different energy levels. So if it makes a transition from n equals 4 to n equals 3, it will emit a photon of the correct frequency. So this is a quick recap of what we've learned about the infinite well. Okay. But there's another aspect to quantum mechanics. We have a space variable. The wave function exists in space. It is spread out in space, but there is also another variable involved. And what is that? That's time. So we haven't talked about time as yet. If this is the wave function, if the electron is in the ground state, this is the wave function. How does this wave function change with time? So this is something I would like to answer today. The wave function, is it static? Is it unchanged with time? If time goes on, then the wave function evolves. The लफ्ज इस्तेमाल होता है मॉडर्न फिजिक्स में, ये सिर्फ बायोलॉजी में नहीं, एवोल्यूशन में. Evolve. The wave function evolves with time. So there is evolution of the wave function. Evolution of the wave function means you have a wave function at a given x at a time 0, because there are two variables. Now if I want to write the wave function in space as well as in time, I use capital psi, if you remember. Okay? Or small psi means just the space part. Capital psi means the position part and the time part. So time changes, and after time t, the wave function at the same position evolves to a new wave function. Wave function has changed. Okay? Like a traveling wave. A traveling wave changes its position with time. If I have a wave like this is a picture of the wave at some time, say at time equals 0. After some time has lapsed, if this is a traveling wave and the wave is moving towards the right, this wave function is going to change its position. So this wave function is evolving. It's changing with time. So how do these wave functions in the infinite well change with time? For this, as you remember, we looked at the Schrödinger equation, and there was a space part of the Schrödinger equation and a time part of the Schrödinger equation. And if you remember, if you can please look up your notes and tell me what the time dependent part of the wave function is. Can you look up your notes and verify this for me? The total wave function psi x of t is a product of a space part and a time part. And the time part satisfies this equation. Is this correct? Please look up your notes. It's good to go down the lane of memory for some time and see what happened in the previous class. So far we have ignored this part, but now let's look at this part. Now you're taking a course probably on differential equations and linear algebra. Have you reached the point where you'll be able to solve equations of this kind? Just started it, okay. So I'll give you an appetizer of what you're going to do in that course. So look at this equation. This is a constant. Energy is a constant because the particle has constant energy. This variable, this function is a function of only time. So if you look at this function and what do you do next? I just do a little bit of rearrangement. So iota h bar d of dt of f of t is equal to E f of t. Okay? I just take ft to the other side. Then what I do next is I take this differential dt to the other side and bring this ft to the left hand side. Iota h bar df over f of t equals E dt.
Hello?
Okay? Just algebra. Now I want to take iota h bar to the other side of the equation. आप सेकंड रो में बैठे हुए लास्ट में आप बताएं if I take iota h bar to the other side what do I get on the right hand side? On the left hand side I get df over f equals, what is this equal to?
मैं इधर से
ओमेगा कहाँ से आ गया?
कौन थी वो? क्या नाम क्या उसका?
E dt over h bar और iota को क्या होगा?
तो पूछ रहा हूँ आपने किसके पास चला गया?
h iota उधर डिनोमिनेटर में चला जाएगा. What is 1 over iota? ये पता 1 over iota क्या होता है? बाकी नहीं पता. बाकी नहीं पता. अच्छा. 1 over iota. किसी को पता है इसका क्या? अगर if I want to take iota to the numerator, can I take iota to the numerator? ये आपने पढ़ा हुआ कभी? ये देखे कभी? अच्छा कोई बात. Let's multiply the numerator with iota and the denominator with iota. So what is iota squared? Minus 1. Okay, so iota over minus 1 is minus iota. So if you want to take iota from the denominator to the numerator, you put a minus sign with it. Okay, so here I just take h bar to the other side, iota goes to the denominator, so this becomes minus iota e t over h bar. Alright, dt. Now, can I solve this equation? Please integrate both sides and tell me what the solution of this equation is. Just integrate both sides. Indefinite integral. is a constant. There's no need for this constant here because दो constant here आपके second order A और B. E square is constant. अब इसको एक्सपेरिमेंट just E is a constant, E is the energy, so it's a constant. So I take the integral of both sides, I put an integral here and an integral here. Well, I've come to the conclusion that it's better to go slow and cover few things than to just go at lightning pace and so that no one understands what's going on. So you take the integral of the left hand side, you obtain natural log f of t. Iota of course is a constant, energy is a constant, h bar is a constant, minus e over h bar, and the integral of dt is just t. And I don't need a constant here because I started off with the second order differential equation and it has already given me the two constants, a and b. So there's no need for a third constant. So if I recast this equation into exponential form, what I obtain is f of t equals, what should I write? Exponent minus iota e t over h bar. So this is the time dependent part of the wave function. Hence, what is the total wave function? The total wave function, which has a position part and a time part, can you please write down the total wave function for me? प्लस क्यों आएगा? So the total wave function is just the space dependent part 2 over L under root sine of n pi x over L multiplied by the time dependent part. Now suppose the electron is in the ground state. It's just in this particular state. Now this is a picture of the wave function at some time. If you see the wave function, if you had somehow access to the wave function itself, remember, you don't have direct access to the wave function. You have direct access to its modulus squared, because that's what you observe in real experiments. So wave function आपके पास का direct access नहीं है, indirect access है. However, suppose you were some supernatural being who had direct access to the wave function, and you take a snapshot of the wave function and you get this pink curve at some time. Now if that supernatural being is not collapsing the wave function and it's taking a snapshot of the wave function at some later time, will it see the same snapshot? Will it see the same profile? No, because there is a time dependent term, and this time dependent term changes the wave function. Now is the total wave function a real number? No, the total wave function has now become a complex number. Okay, because this is a complex number. So if I would like to recast this wave function in the following form, n equals 1 now, I have 2 over L under root sine of phi x over L, because n is 1, and this term becomes cosine of E t over h bars minus iota sine of E t over h bar. I've just expanded the exponent into trigonometric functions. आज कुछ बेकरारी सी है, क्या वजह है? ठीक है, तो ये हमने इस एक्सपोनेंशियल फंक्शन को ट्रिग्नोमेट्रिक फंक्शंस की टर्म्स में एक्सपेंड कर दिया. अब क्योंकि मैंने आपसे वादा किया गोइंग टू गो वेरी स्लो, सो आई एम गोइंग टू टेक दिस टू द नेक्स्ट लेवल नाउ. आई राइट 2 over L under root sine of pi x over L cosine of E t over h bar minus iota 2 over L under root sine of pi x over L sine of E t over h bar. So this is your total wave function. What's the real part equal to? This first term is the real part, and this second term is the imaginary part. And if I would like to put the minus sign with this, okay? So this is the real part and this is the imaginary part. Now can you please plot the real part of the wave function at different times? Please tell me how this real part changes with time. Start off by time t equals 0, then increase time and make a profile of the wave function, the real part of it. Alright, so by the end of this course, you should be able to make these plots with felicity, with ease, with convenience. Because most of my questions are of this kind. You have the ground state, the electrons in the ground state, the wave function is changing with time. I would like to see how is it changing with time. First of all, plot the real part at time t equals 0. ये तो नहीं x के साथ plot the profile versus x at different times. At time t equals 0, this term is equal to 1. So I just have this sine function. This is the profile at time t equals 0. Now on the same graph, I would like you to plot the same profile for different times. If the time goes up, what happens to this profile? Just the first ground state is ये बनाए. अब टाइम बढ़ रहा है. देखो ना, एक साइन फंक्शन ही मल्टीप्लाई हो रहा है. अब इसकी वैल्यू 1 और -1 के दरमियान क्या है? आप बताओ कैसे? ये x है. You don't get additional nodes. क्या हुआ? That's fine. फिर आगे ऊपर चल जाएगा. ठीक है, क्या होगा? What's going to happen is at time t equals 0, this is 1. If time goes up, the cosine function starts moving towards 0. So this sine function is being multiplied gradually by numbers successively smaller and smaller than 1. First it is multiplied by 1, so you get the maximum height. And then the time goes up, this number decreases. It becomes smaller than 1. So but the overall shape remains in space like a sine function. So for longer times, this wave function starts decreasing. The real part of it starts decreasing. It keeps on decreasing. Keeps on decreasing. Still you have nodes here. At a certain amount of time, the wave function becomes flat, and that time equals when Et over h bar is pi by 2. That is time for the wave function to go to 0 is pi h bar over 2e. So at this time, pi h bar over 2e, the wave function goes to 0, and then the cosine function, if time increases further, the cosine function becomes negative. So when the cosine function becomes negative, this wave function remains a sine function, but now it is being multiplied by a negative number. So the wave function starts increasing, but now in the opposite direction. And it starts decreasing further or increasing in the negative direction till it finally reaches a negative maximum. And then cosine becomes negative, but it starts increasing, and then the wave function starts going up and down. So this is a snapshot of the wave function, the real part of it, at different times. So the wave function is actually changing with time. This is a pattern typical of a standing wave. So the standing wave is such that there are always nodes at the ends. For the ground state, there are no other nodes, and the wave function starts with a maximum, it goes down, goes to 0, goes in the negative direction, and it starts oscillating. The wave function starts oscillating. G. Alright. No, we're not going to ignore it. You can plot the imaginary part of the wave function as well. There's nothing special about the real part of the wave function. Okay? There's nothing special about the real part of the wave function. Here I have plotted the real part of psi. So now let's plot the imaginary part of psi. Let's do complete justice to the wave function. Let's plot the imaginary part of the wave function. There's no preference of choosing the real part. What we are actually measuring is the probability density, which is the modulus squared. So the real part and the imaginary part both have an indirect importance, and they are on equal footing. So now let's plot the imaginary part of the wave function. At time t equals to 0, your wave function is 0 because this is 0. Now when time goes up, this starts increasing. Right? The sine function starts increasing. So you get a sine profile which is increasing with time, and the increase is sinusoidal. But there is a negative sign here. So at time t equals 0, you start off, your imaginary part is like this. Can you please turn on the projector? So the imaginary part is straight, time goes up, the imaginary part of the wave function starts increasing but in the negative direction because of this sign. Okay? At 0 time, the wave function is only real. And there is no imaginary part because this term is 0. At a certain amount of time, after a lapse of this time, the real part goes to 0. But the imaginary part has increased or decreased to its minimum value or gone up to its maximum negative value, and then it starts rising again. Eventually it goes up to its maximum value. So when the real part goes down, the imaginary part becomes more negative. When the real part goes to its maximum, the imaginary part becomes negative. So there is a flip-flop of the real and the imaginary part. Okay? So this is a plot of the wave function, the real part of it. And this is a plot of the wave function, the real part of it. Or the imaginary part of it. Now what do we measure in real experiments? What do we see in real experiments? In real experiments, we do not have a direct handle on the wave function. Okay, we cannot directly measure what the wave function is. What we observe in real experiments is, what do we observe in real experiments? The probability density. Okay? Otherwise, quantum mechanics is not going to make sense if you don't observe where the electron is. If you're not going to perform an experiment, you will not be able to tell whether quantum mechanics makes sense or not. So you have to perform an experiment and see where the electron is. And for that, you'll have to take the modulus squared of the wave function, because that gives you the probability of finding the electron somewhere. So if you have this wave function, can you please find out the probability density? Let's denote this by P of x. P. Can you please find out this probability density? Exponent to multiply easy होता है. So the probability density function P x of t equals, you take the complex conjugate of this object. When you take the complex conjugate, this becomes positive. You multiply the exponent of positive of something with the exponent of negative, this term cancels out, and you simply take the square of this. Okay? ठीक है? नहीं समझ आई? So first of all, we know that this is the wave function. Okay? You know this. So let's take the complex conjugate of this. This is real. This is real. Sine of, now n is 1. We're taking n equals 1. Sine of pi x over L. This n is 1 in our calculation. And the complex conjugate of this is, you change the sign of iota. Minus iota becomes plus iota. Plus iota becomes minus iota. Exponent plus iota e t over h bar. Now what do I need to do? I need to multiply the complex conjugate with the wave function itself. So I multiply this function with this function. When I multiply this with this, what do I get? 1. Why 1? Because if I have exponent iota theta and I multiply it with exponent minus iota theta, this is equal to exponent iota theta minus iota theta. This equals e raised to power 0, this equals 1. Okay? 1. So, when you multiply these terms cancel out because you multiply to 1 and you just take the square of these terms. Okay? So, your probability density function is 2 over L sine squared pi x over L. Now, is this probability density a function of time? No. Even though the original wave function, both the real part and the imaginary part, is a function of time, but the probability density, by a fortuitous accident or by luck, it turns out to be independent of time. There is no time dependence in this probability density function. So I can easily write this, I can ignore this time, there is no time dependence, so I don't need to write this time here. I just write P of x. And if I want to plot this probability density function from x equals 0 to x equals L, this is the 0 point. My probability density function is going to look like this, which is the square of the sine. It's just the square of this yellow curve. And this probability density function does not change with time. Even though the wave function is evolving in time, the probability does not change with time. Right? So, ध्यान से बात सुनो, ये बहुत important point है. The wave function is a function of time. It changes with time, but the probability density does not change with time. So if the electron is in the ground state, its probabilities are not going to change with time. This is what is called a stationary state. And this probability density function is what you directly observe in an experiment. You perform an experiment, you have a certain probability that the electron is going to be found in this region. You just find the area under the curve in this small region. You get the probability of finding the electron between these values of x. The maximum probability will occur right in the middle. So the electron, it appears, is avoiding the walls. And this maximum probability of finding the electron at the exact center. But then the electron is not at rest. ये भी एक बात देखें. The electron is not at rest because the energy is not equal to 0. An electron being at rest is not allowed by the uncertainty principle. Because you're confining the electron, it must have some minimum energy. So the electron, it's like a stove, it's like a pan of water. You have a pan of water, you place it at a stove which is at 0 kelvins. So the lowest possible achievable temperature, and still the water is boiling. Okay? So this is the 0 point energy. You have a pan of water and you place it at the coldest possible temperature, where all motion should cease, where there should be no motion of the molecules. Even there, the water is boiling. So there is some 0 point energy. This boiling even at 0 kelvins. So even though the maximum probability of finding the electron is at the center at L over 2, does not mean that the electron exists at L over 2. It means the electron is everywhere. And what you can at best say is, what is the probability of finding the electron anywhere? G. Evaporation is also boiling. Some molecules have a temperature higher than the boiling temperature, so they evaporate. Alright, so if this is the probability density function, अच्छा अब Bohr's model का, देखिए we always have to go back to what we said. ये quantum mechanics एक ऐसा तीर है कि अगर कमान से चल भी जाए फिर भी आप उस तीर को वापस ला सकते हैं। फिर हमें वापस जाके देखना पड़ेगा, क्योंकि मैंने आपको याद है क्लास के शुरू में कहा था कि देयर आर सम थिंग्स यू विल लर्न राइट एट द एंड ऑफ द कोर्स, सम थिंग्स, some affairs that we've been talking about in the pre-midterm era, they start making sense in the post-midterm era. There's some things you learn after the final exam. So really exam is not the ultimate goal in this course, it's your understanding. So if you look at this probability density function, where is the electron? Batao, where is the electron? Just give me a simple layman answer, where is the electron? It's everywhere inside this well. It's inside this well, but everywhere inside the well. हर जाई है। अच्छा, तो इलेक्ट्रॉन का मास किधर है? Where is the mass of the electron? It's distributed everywhere. You don't know where the mass of the electron is. So the mass also becomes diffuse. ठीक है? Because the electron is now a field, the mass is also a field. This is the field of the mass of the electron. Where is the charge of the electron? It's distributed. So the electron has a distributed charge because you haven't seen where the electron is. And is this distribution of charge changing with time? No. The distribution of charge is not changing with time. So when you have a charge and you're not observing the charge, it's distributed in space and it's not changing with time. Then when there is no, would there be some acceleration of the charge? Would the charge be accelerating? If the charge is static, the field is static, means the mass is static, the charge is static, it's spread out, and the probability density function tells you how it is spread out in space. But this is green curve is not changing with time. So is the charge changing its position with time? No, it's not, because the probability density function is constant. Okay? ये बात समझ आई? नहीं समझ आई? अहमद तो जरा इसकी आवाज And that's a very good question. Is the position changing with time? We cannot ask this question in quantum mechanics. It's a good questions that we cannot ask in quantum mechanics are good questions, because you learn by conflict. You learn by asking questions which do not have a direct, easy, accessible solution. So it's a good exercise to ask questions which don't make sense, because then you learn by failure. You learn by counter example. So can we say where? What did you ask? Is the position spread? Is the electron does not have a fixed position? Okay. If you measure the electron to be found somewhere, it does not mean that the electron possesses that location. The electron is everywhere. It does not have a position. There is a realm of possibilities of the position. It's just that when you find the position of the electron, it appears, it collapses somewhere. So its position is also uncertain. The charge is also distributed. But the way the charge is distributed does not change with time. Agreed? The way the mass is distributed does not change with time. Agreed? Because the probability density function is not changing with time. So when the charge is not changing with time, when it's not changing its presence with time, it's like this this room is filled with a very nice perfume, and the perfume bottle has been open for 100 years. So the gas molecules, the vapor molecules have spread out evenly inside this space. Now the distribution of these gas molecules, that is the number of gas molecules per unit volume, is not going to change with time. Right? So the charge is distributed in some fashion, and that distribution is not changing with time. What does that mean? The charge is not accelerating. Right? The charge is not accelerating. If the charge is not accelerating, or it is not redistributing itself with time, there is no way that this electron can emit radiation. Because for the electron or for the system to emit some electromagnetic wave, which is really an electromagnetic field, so you have an electric field which is changing with time. For the electron or for the system to emit some energy, emit some electric field that changes with time, it must have an oscillating charge. A charge that oscillates emits an electric field like an antenna. So there is no redistribution of the charge. This means that this electron that is in the ground state or any excited state, if it remains there, it cannot emit any radiation. Because the probability density function is not changing with time, hence the charge distribution is not changing with time. So this gives a serious blow to the Bohr's model. It's the last nail in the coffin of the Bohr's model. Bohr model कहता था कि अगर electron revolve कर रहा है around the nucleus, it's constantly accelerating, so it must be emitting radiation, and it must gradually fall into the nucleus. Rutherford model कहता था. Bohr model ने इसमें एक ad hoc assumption की थी कि no, if an electron remains inside an orbit, it does not emit radiation. But it's the Schrodinger's picture that lends credence to this postulate, that verifies this postulate or makes sense of this postulate. That if an electron remains in a precise energy level with a fixed energy, its probability density function cannot change, does not change. It's a stationary state, so it cannot emit radiation. So an electron inside a precise energy level is not emitting radiation. And if an electron is in a precise energy level, is there any uncertainty about the energy? No. There is no uncertainty about the energy because the energy is fixed. It's E, it's E, it's E. The energy is fixed, you know what the energy is. But the problem is that you can't measure this energy because the electron remains in the orbit forever, remains in the energy level forever. This is also in accordance with the uncertainty principle. You precisely know what the energy is because the electron remains in that energy level for infinite, for eternity. So this is also in accordance with the uncertainty principle. Alright, so I have a simulation to show you what all of this is actually meaning. G. Right. So the question this gentleman has asked is, how is this probability density related to the charge and the mass? You're asking very insightful questions today, and welcome to the class. Alright, so what is this a probability density function of? This tells you, if this is space, where can you find the electron? So this is telling us the potentiality of where the electron can be found in an experiment. So before the experiment, the electron is everywhere in this region. So if the electron is everywhere, charge is a property of the electron. So the charge is everywhere. The mass is everywhere. But how is that charge distributed? It should be proportional to the probability density function. If there's a peak here, then there's high probability of finding the charge here. So this probability density function tells us the probability density function with respect to x, the probability density function with respect to charge. Okay, so this is how charge is spread out. This is how mass is spread out. But the only problem is that once you make a measurement, it collapses. So you'll never find out that a charge of 0.5 into 10 to the minus 19 coulombs. There's no smaller charge that will ever measure smaller than 1.6 into 10 to the minus 19 coulomb. The charge of an electron is not destructible. It's the smallest unit of charge. ठीक है, इससे छोटी इकाई ही आपको मिलेगी। तो अब ये ना समझना कि इससे छोटा चार्ज आपको मिलेगा, क्योंकि कुछ चार्ज हम यहाँ ढूंढ लेंगे, कुछ यहाँ ढूंढ लेंगे, बिकॉज व्हेन यू मेक अ मेजरमेंट ऑल ऑफ दिस चार्ज bunches up, it gathers up, parcels together and impinges on a detector. The mass bunches up, congregates and pinches on a detector. Okay, let me just go on a little bit. Alright, so here what we are observing is, alright, be attentive please. This is the proper way of learning quantum mechanics. Calculations is not going to do the task unless you don't understand what's going on. So we have an infinite well, and inside this infinite well we have multiple energy levels, and we say that the electron is in the ground state, the first energy level, which means n equals 1. And we also notice that the real part of the wave function is given by a sine function, and the imaginary part at time t equals 0 is just 0. But the probability density function looks like this. This is something we've actually seen on the blackboard. We've drawn these plots on the blackboard. Now what I'm going to do, I'm going to change time. These plots, these are the wave functions, the real and the imaginary part. Red is the real part, blue is the imaginary part, and this is the probability density function. Now this is the time. This picture is frozen in time. It's at time t equals 0. Now I'm going to run this simulation. The Schrödinger equation has been written at the back end of these programs. It's a JavaScript. Now the Schrödinger equation is actually solved numerically as time progresses, and we want to see what happens to the wave functions and what happens to the probability density function, because you would like to believe whatever I say. You shouldn't trust me per se. So let's run this simulation, change the time. So what you're observing is that the imaginary part of the wave function is going towards the negative side. The real part is decreasing. Nothing happens to the probability density function. It remains where it is. So nothing happens to the distribution of charge, nothing happens to the distribution of mass. An electron that is in a ground state or in any state has fixed energy. Fixed energy means it always remains in that state because delta E, delta T, they are conjugate variables. Fixed energy means the time for which it lives in that state is infinite. And this also means that it cannot go down to a lower state or make a transition to emit a photon. The charge distribution is constant, hence it cannot emit any radiation. So everything is making neat sense. The complete picture is completing. Now the real part is going towards the negative side. It's going towards 0. The blue part is going towards the maximum negative, and then the real part is going down, and the blue part is starting to go up. And the variation in time is also sinusoidal. So if you notice that these functions appear to move faster near the baseline and slow at the edges. That is why when the sun is setting and when the sun is rising in the morning or setting at the time of Maghrib, it appears to move faster because that's a property of the sine function. You take the slope of the wave of a function, sine function, it's 0 at the maximum and minimum values and it's maximum at the 0 crossing. So it's the same effect that you are observing. So now you have a fair idea of how the real and the imaginary parts are changing with time. Now there is another way in which I can show this graph. I don't know which one of this makes more sense. I think this is makes more sense, but there is another way of showing this graph to you. एक मिनट I'm going to make it run a little bit faster. So this is another way of showing the same results. This is the probability density function remains constant with time, it does not change with time. Here we are plotting the modulus of the wave function. I mean the absolute value of the wave function. So is the absolute value of the wave function changing? This is the wave function, this one. Is its magnitude changing with time? The magnitude. No, the magnitude is not changing with time because this is not changing with time, this is not changing with time. The magnitude of the exponential function is always 1. Okay? So the magnitude of this wave function is not changing with time. However, the phase is changing with time. So these colors show the phase. So it becomes blue, cyan, magenta, green, and so on. Because positive, negative, positive again, and then negative. So the phase is being shown by the color, and the amplitude is just the contour. So what is more intuitive for you to understand? The previous one. Okay. So now let's look at the first excited state. What happens when the electron goes to the first excited state, to the n equals 1 state? How many nodes do you expect, or how many lobes do you expect? I mean, now there's going to be 1 node at the center and 2 lobes of the probability density function. Okay? So now let's go to n equals 2. Alright, so this is the first excited state. What is happening in the first excited state? If you look at the red part of the wave function is, of course it has a node at the center, nodes at the walls, and the wave function is changing like a sine function, the red part. Just look at the red part for the time being, only the red part. If you look at the red part is a sine function, it's going up, down, it's changing its direction. The blue part is also changing its direction, and it's always 90 degrees out of phase with the red part, which means that the red part goes maximum, the blue is 0. The red part goes negative, the blue part is 0. The blue part goes maximum, the red part is 0. So the real and the imaginary parts of the wave function, they are changing. It means that the wave function is changing in time. It's evolving in time. However, if you find out the probability density function, the probability density function does not change with time. It's constant. So if the electron is in the first excited state, you will never find the electron at the center of the well. You will never find the electron at the walls. You will find it with maximum probability at 1/4 of the length and 3/4 of the length, and with some finite probability in between. And what's the area under this curve? It has to be 1. So this is when the electron is in the first excited state. The wave function is changing with time, but the probability density function does not change with time. So when an electron is in the first excited state, can it emit radiation? No, because there is no redistribution of charge. The charge remains, the distribution, the profile of the charge remains where it is, hence it does not accelerate. So let's look at an even higher excited state. So this is n equals 6. The fifth excited state. Once again you observe that the probability density function remains constant with time, it does not change with time, and these wave functions are now oscillating. Why are they oscillating? Do they seem to be oscillating at a higher frequency, the wave functions? First of all, compared to the n equals 1 state, are these wave functions, do they appear to oscillate at a higher frequency? Why is that? Why is the apparent frequency of oscillation of these wave functions higher? Because the energy is higher. Since the energy is higher, this energy, this energy is actually E over h bar is some frequency. So this is the frequency of oscillation of the wave function. Even though there is no photon being emitted, the energy is precise, the frequency is precise, there is no photon being emitted, remember that. But the amplitudes themselves, the wave functions themselves, they are oscillating with higher frequencies. But the overall profile of what you observe in an experiment does not change with time. Now something very strange is happening here. You have these multiple nodes. For n equals 6, you have how many nodes? 1, 2, 3, 4, 5. Excluding the walls, you have 5 nodes. For the nth stage, you have n minus 1 nodes, excluding the wall. If you go to even higher excited states, you get more and more of these bumps. So the last thing I would like to show you now, and then we'll derive this expression in the next class, is the following. Suppose, very important point. This is one of the most beautiful points in this course, most beautiful junctures. Suppose you have an electron that is in both two energy levels at the same time. It's in a superposition. Okay? We know that superpositions exist. You've done a whole homework on this. You know that superpositions exist. You know in the interference experiment that the electron can pass through both slits at the same time, in a way, because the wave function is smeared out. Now suppose the electron is in the ground state and the first excited state at the same time, which means it's in a superposition. So its wave function is the sum of the wave, this wave function and this wave function. Now I'm just going to show you the plots and we'll derive on the blackboard what we see on the plots and see if a photon is actually emitted in that case or not. I call this the moment of truth. As a teacher I find this the moment of truth, as a student I don't know. So without computers, modern physics cannot be taught well. It cannot be taught at all, in fact, in the modern world. Alright, so you have an infinite well, and now the electron is in a superposition of the ground state and the first excited state. So it has a wave function that is a combination. Now what's going to happen, if you look at the real part is changing and the imaginary part is also changing. But they're changing in such a way that the probability density function is also changing. So this is like an African camel with two humps. So the camel is filling water in one hump, the other hump is exhausting, and then the other hump is filling up. So one hump goes down, the other hump goes up, this hump goes down, this hump goes up, and now the probability density function is changing with time. And we'll observe in the class tomorrow that this frequency of this change in the probability density function is just equal to the energy difference between these levels, and this is the frequency of the photon that is emitted. So inshallah see you tomorrow on Thursday, and we're going to have a demonstration on Friday on tunneling.